Hello and welcome. A fuel that burns without emitting carbon oxides is the Holy Grail. Carbon-based fuels emit carbon dioxide, resulting in the greenhouse effect and eventually climate change. The search for non-carbon fuels continues. Fuel in the form of power from lithium batteries has made possible electric vehicles requiring no petrol or diesel. Lithium battery-powered aircraft do exist, but for larger aircraft flying longer distances, the batteries are too heavy to be practical. What is needed is a non-carbon fuel that is plentiful. You don't have to look far to find such a fuel, for hydrogen is the most abundant element in the universe, making up more than 90% of all elements. Indeed, the product of its oxidation makes up 71% of the surface of the Earth. Yet, free elemental hydrogen on Earth is rare. Hydrogen that enters the atmosphere rapidly escapes Earth's gravity due to hydrogen's low density. Hydrogen is either sourced by electrolysis of water or from natural gas. The environmental credentials of the processes is in the name. Renewable electricity from solar, wind or hydro that is used in the electrolysis of water gives us green hydrogen. This is environmentally the best. Blue hydrogen is when natural gas is split into hydrogen and carbon dioxide either by steam methane reforming or autothermal reforming, with the carbon dioxide being captured and stored. The environmental impacts on the planet are mitigated. Natural gas is relatively cheap and abundant. Grey hydrogen has been produced for many years in a process similar to that of blue hydrogen, but the carbon dioxide is released into the atmosphere. That is bad for the planet. So-called pink hydrogen is made via electrolysis using nuclear energy. Yellow hydrogen is made when electrolysis is achieved with solar power alone. Australia has abundant sunshine. Investor Andrew Forrest has announced plans to manufacture hydrogen in Australia. The challenges are plenty. Storage and transport of hydrogen, for instance. 1 litre of hydrogen gas at normal temperatures and pressures weighs just 90 milligrams. Chilling hydrogen gas to minus 253 degrees centigrade will bring it to a liquid state at atmospheric pressure. Even so, this liquid's density is low compared to that of other fuels. Liquefied hydrogen can be maintained at 50 atmosphere pressure in pressurized and thermally insulated containers. 1 litre of liquid hydrogen weighs 70 grams, being 778 times greater than its gaseous form. 1 litre of jet fuel weighs 804 grams, making it 10 times denser than liquid hydrogen. A comparison on how much energy can be obtained from each litre of the fuels must be made. Liquid hydrogen will provide 2.36 kilowatt hours per litre of energy. Jet fuel will provide 10.4 kilowatt hours per litre. In summary, jet fuel can provide 4.4 times the energy compared to an equivalent volume of liquid hydrogen, but liquid hydrogen is 11 times less heavy. An A380 aircraft holds 320,000 litres or 257,280 kilo of jet fuel on takeoff, a fuel that will provide 3,328,000 kilowatt hours of energy. To provide this same energy, there would have to be 1,410,169 litres of liquid hydrogen on board instead. To do this, the fuel tanks would need to be 4.4 times larger. Larger fuel tanks of liquid hydrogen in the A380, yet that fuel would weigh just 98,712 kilos. That is a massive 159 tonnes less weight for the A380 to carry. Hence, the A380 would burn less fuel, so needing less fuel to carry and smaller fuel tanks. How much smaller? If you know, leave a comment. So, there is the challenge. Engineers, is liquid hydrogen the future of fuel for aviation? It sure looks promising to me. Hitting the subscribe, like and notify bell helps out.